Your running data set is looking a little wonky. I think you got to apply the Kalman filter. Kalman filter, capital K-A-L-M-A-N, space F-I-L-T-E-R. Kalman filter. Our engineering term of the day is actually two words, Kalman and filter, but engineers will generally hear those two words together. If you hear the word Kalman, the word filter comes right after it all the time. So I'm treating it as one important engineering term. To understand what it means, let's break it down into two parts. The first part is Kalman with a capital K, so it's a proper noun. And that word Kalman comes from the last name of a Rudolf Kalman, a guy named Rudolf Kalman. He was an American electrical engineer, Hungarian born, so his last name is Eastern European. And this American engineer and professor, he passed away in 2016, but he left us engineers and scientists and data people and everybody, he left us a cool tool for analyzing and understanding large sets of data better. So Kalman comes from a person, and then that second word, filter. What's a filter? Yes, we know that a filter can purify the air, but that is not the type of filter that we're talking about here. We're actually talking about a filter that is an algorithm. It's an algorithm for cleaning up or simplifying or reducing the error in a bunch of data. If you have a long string of data, a filter will help clean up that data if you have errors in it. And this guy, Rudolf Kalman, gave us a specific type of filter that cleans up data pretty well. So well that so many different engineering fields use it today. What is a Kalman filter then when you put those two words together? It's a special algorithm that cleans up data pretty well, and it works by doing two main things. One, it predicts data based on some kind of model, maybe a physical model or a mathematical model or past data. It has some information from which it can predict data. And then the second thing that it does is it measures real data right now. It's not just relying on a physical model. It's actually taking some sensors and measuring the data right now. And it puts those two things together. It sees how different the predicted data is from the measured data. And it says, okay, when there's very little difference between the predicted data and the measured data, we're going to trust this measurement. And for other measurements where the predicted data is pretty far off from the measured data, we're not going to trust those measurements as much. NASA used Kalman filters to help with flight control systems because flying, a spaceship especially, requires a lot of data. It's not just one single data set. You're measuring air pressure, air speeds, flight speeds, thrust, lift, gravity and weight, and all sorts of different things. All this data is coming in all at once in real time. And based on this real data, we can compare that real data to some physics models and physics equations and see how far apart we are from the predicted data. And maybe it turns out that air pressure is not something that we can predict very accurately, so we aren't going to trust that data very much. But instead, when we measure our vertical velocity or something, our predicted model really matches our measured data really well. Well, we're going to trust that data. And the Kalman filter integrates all this stuff. It integrates this trust in our different data sources and helps us come up with a nicer data set. I used the Kalman filter in biomechanics too. We had to measure how people walked to do some diagnoses and treatments of patients. For example, a cerebral palsy patient might not have good nervous system control and muscular control, and so they might walk in a specific way, and we need to measure that. We might look at ankle velocity or the angle that the knee makes while they walk over time, or we might have electromyography measurements looking at the activation of the quadriceps muscle firing over time. So basically, there's tons and tons of data you can take when you measure how somebody walks. And it's noisy. There's lots of error that can happen. I mean, if a patient starts sweating a lot, for example, the sweat gets in between the skin and the sensor, and that can start screwing up our data. So we need a way to try to manage the error that we see in our data. And that's where a Kalman filter becomes really useful. We have our scientific models, and then we have our real sensor data, and we need to reconcile the two. And it's not the only type of filter. There's lots more filters coming out from this. This is a cool field, data analysis, and Kalman filters are a big tool in that field. That is our engineering term of the day, Kalman filter. Hey, this is your host, Pius, telling you to not filter out this noise and keep on listening to and subscribing to the Engineering Word of the Day podcast. If you like this type of stuff, you should also listen to the longer podcast called the K-12 Engineering Education Podcast, which is all about bringing engineering education to all people. Go on over to k12engineering.net to check it out.